Okay, so today I'm going to introduce you a third way of designing a processor. We talked about single cycle design and multi-cycle design. I'm going to talk about the pipeline design now. So we have seen that there is certain difference between single cycle approach and multi-cycle approach, in the sense that multi-cycle screen not visible. Okay, let me go back and share it again. I think I'm seeing somebody's screen. Rohit, how did that happen? Okay, now it seems to be in normal state. Is it visible now?
Yes.
Okay. Okay, so after talking of two approaches, single cycle approach and multi-cycle approach, uh, we are going to talk of pipeline approach today. So the difference between these two approaches was essentially that multi-cycle design approach tries to get better performance as well as better resource utilization. So we will see that the pipelining approach can improve the performance even further. But we would need to understand what are the limitations of this particular approach. Okay, there are certain kind of hazards which come into place, and we'll briefly try to see how to handle those hazards, how we can remove those, or how can we reduce the effect of these hazards. So here is a simple illustration of how these three different approaches compare. So in a single cycle design, the data flows through various stages. I'm taking example of a DP type of instruction, which goes through instruction fetch, then decode or register read, then execution and write back. So there is uh, starting from the PC program counter back to the write back stage, there is a complete combinational path which it encounters. So information is flowing through these stages, and at the end of the clock period, the state change happens. So state change could be in a register file, it could be in flags, it could be in memory, or any combination of these. Okay. The problem with this design was that the slowest instruction pulls down the clock frequency and resource utilization is poor. Uh, there are some instructions which are impossible to be implemented in this manner, which inherently require sequencing, uh, either because things have to be done in certain sequence, or the module used don't allow something to be done concurrently. So we went for a multi-cycle design where the path gets divided into various stages, and after every stage we have a clock which uh, stores the result of that particular stage. So at the end of first clock, you have instruction fetched, then operands are fetched, then the result is produced of addition subtraction, and then the result is stored in register file. So it takes multiple cycles. In this case, we had 4 cycles for 4 different micro operations. So clearly here actions are split into multiple steps. Each step takes one clock cycle. And you have to have register which hold the intermediate values. So at the end of every cycle or every step, the value gets stored. All instructions need not take same step. That's where the time saving comes. But the clock frequency here gets decided by the slowest step. So if the timing of various steps are not balanced, then we'll have some time wastage. Okay, so we resort to splitting the steps or combining the steps so that the timings are balanced. Here resources can be shared across cycles. So compared to the single cycle design, we could eliminate the adders. Instead of two memory modules, we use single memory module. And for this kind of sharing, we need to incur the cost in terms of multiplexing. So improving the design further with pipeline uh, is possible if resource saving is not an important issue. We are focusing more on performance. Uh, so in pipeline design, basically we allow instructions to overlap in time. So before letting one instruction finish, we try to start the next instruction, and before that is finished, yet another instruction, and so on. So you see that a chain of instruction is following each other. Okay. Ideal thing would be that in every clock cycle, we introduce one instruction into pipeline. If it can be done or not, that is something we will examine, but that is the ideal situation. So if that happens, then effectively the rate at which instruction are executed could be taken as uh, one cycle per instruction or one instruction per cycle, whichever way you may like to look at it. So there is a difference how resources are getting utilized in various approaches. In single cycle design, each resource is tied up for the entire duration of the instruction execution. In multi-cycle design, resource utilized in cycle T of instruction I is available again for cycle T plus 1 of the same instruction. Okay, for a given instruction, a resource could be utilized multiple times in various cycles. In pipeline design, the resource utilized in cycle T of instruction I is available again for cycle T of instruction I plus 1. Okay, so if ALU is utilized in third cycle of one instruction, the next instruction can also utilize ALU in its own third cycle, and so on. One compact way of comparing these three approaches is in this two-dimensional space, where on one axis I'm showing cycle time or the clock period. On the other axis, we look at number of cycles required per instruction, or CPI, cycles per instruction. So where do we place single cycle design? Single cycle designs require long cycle time. Okay, cycle per instruction is low. You have just one cycle per instruction, but that cycle is large. Multi-cycle design, the cycle time is short. Okay, it needs to cater for one basic step, not the entire instruction, just one basic step. But now the CPI is no longer one. CPI could be 2, 3, 4, 5, whatever, depending upon how complex your instructions are. Uh, Pipelining approach tries to get best of both. Okay, ideally you have CPI of 1. Okay, if you are able to continuously run your pipeline, you get CPI of 1. And the cycle time is similar to what you have in multi-cycle design. Okay, because again you are catering for one basic step or one micro operation at a time. Any question at this stage?
So like in the multi-cycle design that we saw that like for all instructions we have the same number of cycles, right? Like for branch also we have to do those 5 steps.
No, no,
And
that was not true. For a branch instruction, we started with just a 2-cycle design, but in order to combine some states, we made it to 3. Load instruction, for example, took 5 cycles. Store took 4 cycles. DP took 4 cycles. And we also saw that more complicated DP instruction where shift is there and uh, shift amount is specified by the register, you could even take 6 cycles. So different instructions take different cycles in a multi-cycle design. And usually one would refer to an average CPI in such a case. Average CPI would be somewhere between the min and the max, depending upon what is the proportion of different types of instruction which you encounter in a program. So those averages are program dependent, not they are not something which you can talk of independent of the programs.
okay, sir.
So
Sir,
when we hear about instructions for clock from Intel or AMD or something like that, so sometimes I think it's more than like one though. Like, so how is that achieved? Because that's IPC of less than one, like CPI of less than one. Then
CPI of less than 1, yeah, we'll talk of that also. So how do we get CPI of 1? Basically, you try to do many instructions concurrently. So we'll talk of that also. There was another question. Somebody started speaking, but
yes, so that was the same question. Why, how is CPI 1 in pipeline design?
okay. In pipeline, CPI is if you look at individual instruction, it will go through several stages of pipeline and spend that much time. Uh, but if you look at this collectively, the rate at which instructions are being processed is 1 per cycle. Okay. So assume that you have a long stream of instruction and they are just being pushed into the pipeline every cycle, then the effectively you have CPI of 1. If you want to look at the transient situation when starting with an empty pipeline, you are starting filling it up, okay, and then at the end you drain the pipeline. So if you account for that, then of course it would be more than 1 because initially and towards the end there are periods when um, pipeline is partially full. Okay, we'll see that there are other reasons why CPI equal to 1 does not get achieved. Okay, we'll see that, but ideally, if you have let's say infinite stream of instruction, the pipeline runs with a CPI of 1. Okay, so now, so that was the concept. Now let's try to see in terms of circuit how you will get a pipeline design. So here is the usual circuit, single cycle data path. I'm calling different stages with these names. IF, instruction fetch, instruction decode. Although the primary activity, as you see here, looking at the circuit, is the operand fetch, but it's called the instruction decode stage traditionally. Execute, memory access, write back. So below write back, you don't see anything. So write back is actually happening in the register file, but conceptually we are writing write back at the end like this. So in pipeline data path, since we are not trying to share the resources, all we need to do is put these registers, which look like walls, separating these stages. Okay, so everything which goes across the stage goes through register. So in every stage of pipeline, you have input coming from the register on the left and output going to the register on the right. Okay, so everything propagates like a wave through these registers. So starting from PC, uh, if you focus on one instruction, the instruction gets stored in this register. Also, we perform PC plus 4, so that result also gets stored here. Then whatever we are doing in second cycle, the results are getting stored in this register. One could actually see this only at conceptual level. Physically, each of these wire would be going through a register of certain size, depending. Let's say here you have, I think these are 24 bits, so they go through a 24-bit register. This data is 32-bit, so that goes through a 32-bit register, and so on. Okay. So as the first shot, this is our pipeline design. But we want to fetch, if we do this way, then this PC plus 4 is coming to the PC much later after going through several cycles. Since we want a new instruction to be fetched every cycle, output of this adder is fed back to PC immediately. Okay, so at the end of first cycle itself, PC will get the new value. Okay, so that allows next instruction to be fetched in the next cycle. Okay, so that's a change which is essentially required. Another thing we need to correct here is that write back is happening in the last stage. Okay, but in the cycle when we are writing the result, we should have the correct write address here. So if in this current scenario, we have the data coming from an instruction which has reached its WB stage. But at that time, there is some other instruction which is in the ID stage. Okay, so it will be a mix up. The write address coming from one instruction and the data to be written coming from another instruction. So the correction required for that is shown here. That write address also travels with the instruction through these registers, and the data and the address both are made available to the register file correctly. Okay. So this is an important point. I hope it is clear. Any question on this?
Sir, how are we handling this issue for that the mix-up of instructions?
Yeah, what we are doing is that the write address which comes from the instruction is also made to travel through these registers. So that means it's getting delayed. Write address. So as the instruction is going through this phase, the operands are read, and this offset is also latched here. The write address is also latched here. So any information which you need, you keep propagating through these registers. Okay, so it is kept delay. It keeps getting delayed one by one in every cycle, and the address and data are coming here together.
Okay, so data and write back address are parallel both after the ID instruction. Okay, okay.
Yeah.
Wouldn't this cause an issue in branch instruction?
Sorry, can you be a bit louder?
Like, how would branch instructions be executed? Because like wouldn't the address would take some time to change and
Yes.
the next.
Yeah. That's a big problem. So I have carefully avoided talking of that. I'll come to that shortly. So let's leave out branch instruction for the moment. That needs special care. But for instruction which let us say instruction which write into register file, these are load instructions and DP instructions, some of the DP instructions. So we carry the right address. Everything which is pertaining to an instruction is kept together, okay, and everything moves to the next stage. Everything moves to the next stage, and so when it comes to write back, you have the data and address together.
Sir, here we changed the we changed the register sizes because of PC. So only when we add four, only for those kind of instructions, the next instruction will be ready in the after one cycle, right?
Yeah, excluding branch instructions, let's leave out branch instruction. The next instruction address for next instruction is PC plus 4. So while the current instruction is getting fetched, we are computing PC plus 4, and at the end of the cycle, we have the new PC address and the current instruction is moved to the next stage.
Yes, sir, understood.
So PC would need to have multiple things, right? Because we're not just calculating one next instruction, we need to calculate 4 or 5 depending on how many stages there are.
In every cycle, we are again, let me emphasize, suppose we don't have branch instruction, you just have sequence of non-branch instruction. So in every cycle, you are doing PC plus 4, PC plus 4. So PC is continuously incrementing every cycle and causing a sequence of instructions to be pushed into the pipeline.
So, but this is assuming that every instruction would get executed correctly within the pipeline thing without any errors. Like if there are two instructions which need to be solved one after the other, like I'm writing to one register and then in the next one
Yeah. Okay,
that.
I'll come to that again shortly. So when I say ideal pipeline, it means that the instructions were independent. There were no branches. Okay, you were executing instructions in this order was absolutely correct. Then we could keep feeding instructions one by one every cycle. Yeah.
So I think it will have to do with the size of the registers that we have. Like we could have the size of the register divided by the size of an instruction, number of instructions per cycle in the pipeline.
Size of register.
Yeah, because you would need to store the instructions, right?
Okay, let me talk about size of instruction. So at the end of first cycle, what we are storing here is just an instruction. So this will be 32-bit register. After ID stage, we are storing this offset, this operand 1, operand 2, and extended offset here, plus the write address. So the size of this register is 24 plus 32 plus 32 plus 32 plus 4. Okay, this is only register number. The size of register here is 32-bit output of ALU. This register contents, so another 32-bit register address 4 bits, and so on. So you, although I've shown these of equal height, the registers are of different sizes.
And so like the one with these registers which are shown in green, so actually there are different registers. Like suppose for a particular place, 5 different registers.
Yeah, these are different. Yeah, so this it could be either way. You could think of this thing as a one single huge register or separate registers. They'll all be clocked at the same time. So it doesn't really matter whether it's a single register or separate registers.
I'm sorry, here ID/EX, the register between that, those two instructions. So why do we need that? Like all the instructions are getting to the next stage simultaneously. So why do we need to delay that?
These registers are required to hold the information which was output of ID stage. Okay, so that the next thing can come into it. So think of these as chambers in a building with doors. So you have something in this chamber. It crosses this door and comes to this chamber. Then it crosses this door and comes to this chamber. So at the clock edge, the stuff moves from here to here. The stuff here moves to the next chamber and so on.
Yes, yes, sir. If it directly goes to the ALU, then how would it like? Why would it affect?
Okay. Uh, then if things change here, then things will change there. So there is a sort of kind of short circuit. There's no isolation between these. Uh, if changes occur here, they'll immediately reflect in the next stage.
Yes, got it.
So you need to isolate these. ALU is acting on the data which is stored in this register. RF is responding to the addresses which are coming from the instruction which is here. Okay. ALU is acting on data which was fetched from register file in the last cycle.
Yes, got it.
Okay, can we move? So these are complex diagrams. So when you analyze the performance of a pipeline at a somewhat higher level, you draw these like this in somewhat abstract manner. So you could draw simple diagrams where you name the stages, put the stage name like instruction memory, register file, ALU, data memory, and so on, and some symbolic interconnection. Or you show like these blocks indicating the action: instruction fetch, instruction decode, execute, and so on. So either way, you can draw these, and it helps in analyzing the activity in a pipeline, as we'll see in some examples. So we also indicate usage of different stages by instruction. Here I've shown those 5 stages, and the shaded part indicates uh, which is the active part. Okay. In a storage element like memory or register file, the right half is used to indicate the reading activity and left half to indicate writing activity. So for example, load instruction, you do read in instruction memory, then you do read in register file. ALU is a combination circuit, so entire ALU we shade. Data memory, you are reading, so right half is shaded. Register file, you read, you are performing write, final write back, so left half is shaded. Okay. Store instruction, read here, address computation, and then write. Add or DP instruction, read, ALU operation, skip this and do write here. Branch, you perform a read, do nothing here, do address calculation, and that is it. Okay, so now when you want to analyze action of multiple instructions, there are 2 representations commonly used. In one representation, the horizontal axis indicates time and vertical axis indicate a sequence of instructions. In another one, horizontal axis represent pipeline stages and vertical axis represents time. So let me illustrate these two. This is the first representation. each vertical line would correspond to one time instant. So time t, t plus 1, t plus 2, and so on. The time is being counted in terms of clock cycles. And this row corresponds to how instruction I behaves. Next is how instruction I plus 1 behaves, and so on. So what we are saying here is that ith instruction goes through these 5 stages in time slots t, t plus 1, t plus 2, t plus 3, t plus 4. The next instruction, or I plus 1th instruction, is in IM stage at time t plus 1, RF stage at time t plus 2, and so on. So it's lagging behind I by 1 cycle. Similarly, you have I plus 2 here, I plus 3 here, and so on. So this is one way of looking at a sequence of instruction and what they are doing at different instants of time. Another approach is that the time is now on the vertical axis. So at time t, which instruction is in stage IM? It is ith instruction. And which instruction is at stage RF? That is I minus 1th instruction, and so on. So if you need to focus on one instruction, let us say instruction I, it is at IM at time t, at RF at time t plus 1, in ALU at time t plus 2, and so on. Okay, so each horizontal line is a snapshot at a particular time, and it indicates different various stages of the pipeline and which instruction is sitting at which stage. Okay, so this allows you to visualize a sequence of instruction over a sequence of time instants. Now let's look at the hurdles or hazards in instruction pipelining in this manner, which allows us, which actually prevents us from running the instructions continuously with the CPI of 1. So there are 3 types of hazards: structural hazards, data hazards, and control hazards. Structural hazards come because of resource conflicts. If there are 2 instructions which require the same resource in the same cycle, then there is a conflict. In the simple case we have seen, there was no resource conflict, but there could be. Data hazards come because of data dependencies. One instruction needs data which is yet to be produced by another instruction. And control hazards are there because decision about next instruction needs more cycles. Okay, so you cannot continuously run the instructions. So let's examine these in little more detail. In the present design, as I mentioned, there are no structural hazards because there is no resource conflict. We have kept separate data and instruction memories. If we had combined the memories for instruction and data as we did in multi-cycle design, then this problem would occur, that one instruction is getting fetched while a previous instruction is trying to do data read or write. We also retain the address for PC incrementing and branch address calculation. If everything was to be done with ALU, then there could be again a conflict. So we ensured that each instruction uses ALU and any other resource at most once in one cycle. So in that sense, actually, the pipeline we have just discussed is called a linear pipeline. That instruction just flow in a linear order. If you have nonlinear pipelining where instruction moves back and forth among stages in order to reuse something, then it is a nonlinear pipeline. And that's a cause of some structural hazards. Also, we have separate read-write ports in register file. So one instruction can read from register file while other can write into it at the same time. Otherwise, that itself could be a cause of conflict. Okay, now let's look at the So just before I move to this, so structural hazards can be avoided by providing sufficient resources. So that is how it is handled. Let's look at control hazards. Suppose you have an instruction, which is a branch instruction, and at this point you test some flag and either continue to I+1 or start with instruction L. So here is instruction I, which is going to go through these stages at different times. Instruction I+1 should normally get fetched at this point, okay, and I+2 at this point, and then I+1 should come to RF stage. But we can't unless we decide whether the flag is true or not, whether the condition is true or not, and we compute the address where you have to branch in case the condition is true, you don't know what is to be done. So if branch has to take place, then the earliest you can start is here, because if you're using ALU for address computation, the target address is available only here, and you can start your target instruction at this point. So you can see that there will be a delay of 2 cycles. For 2 cycles, you are idle. Now, if branch is not to take place, when can you decide? So you can well, you would have PC plus 4 at the end of the cycle, and you can look at the flag and start execution here without losing any time. But if branch has to take place, then you lose 2 cycles and you start 2 cycles later. Okay, now let's look at data hazards. Suppose there is an instruction which is loading something into register R6. The next instruction uses R6 as an operand. So we look at the timings. Instruction I is spread over these cycles, and it's in this cycle R6 will be filled up. Okay, so instruction I+1, you can't, if you start here, then at this point you are trying to fetch the operands, but the operands have the old value, so it will not be correct. You need to delay. Even at this point, the operands are not having their correct value, so you have to delay further. Strictly speaking, if you are taking entire cycle for, I mean, if you are writing to register file at end of the cycle, then you have to wait even further. But typically, register file timings are such that you can actually write in the middle of the cycle. So you can have a 2-phase clock, or you can clock register file at the other edge. So you can split the cycle into first half where you do the write and second half where you do the read. If that is the case, then R6 get written here in this cycle and read by the next instruction, that cycle. You'll have a delay of 2. Okay, 2 cycles you have wasted where you have to wait for availability of the result. If you can't have a read following a write within the same cycle, then you will have a 3 cycle delay instead of 2. But I just want to say that this depiction is slightly incorrect, although the delay is 2, but the correct way of depicting is like this. That second instruction has been fetched. Okay, it's not that we delayed the instruction fetch. Instruction gets fetched, but we hold it in the RF stage itself. Okay, so that is the correct indication. So second instruction has come into the pipeline, and it remains stuck in the RF stage. And only when the data is available, you proceed further. Yeah.
How is this exactly implemented though? Because I don't think like the program has to be intelligently aware of if something is causing a data hazard or not, or if something is causing a control hazard. So like, do we go back on and do we like decrease the PC by 2 by 8 to go back 2 instructions or something like that, or exactly what happens here?
Yeah, we will see how we control this, how we ensure that instruction does not read the wrong results. So there are things which can be done in hardware, there are things which can be done in program. So we'll talk of that. So right now, what we are concluding out of this is that an instruction needs to wait at some stage before it can proceed. Okay, how we achieve that, we'll see later.
So like in the previous one, like the correct way would be to read R6 after it has been written, right?
Yeah.
Okay.
So small trick which I have introduced here is that the writing into register file finishes in middle of the cycle. Okay. So that by the end of the cycle we can read.
So is this done by using different edges of the clock? Like you write on the rising edge and then read on the falling edge?
It can be done that way, yes. Okay, so let us try to see the same thing in the other view where time axis is shown vertically. So at time t minus 1, this is where the instructions are. Okay, instruction I is here. That is the load instruction. And we will see how it moves as the time passes. So normally the sequence will continue like this. At time t, instruction I is in ALU. But now this instruction we have to hold back in RF stage itself. Instruction I plus 1, which is that instruction. Not still finished with RF. Okay, so we introduce a no operation here. So idle just feed some zeros to this ALU, and we need to do that for one more cycle. Okay, now at this point at t plus 2, instruction I has reached the write back stage. Okay, meanwhile there are two no operation. These are commonly called bubbles. So we have introduced bubbles in the as if fluid was flowing into a pipe, and we introduced these air bubbles into it. So two bubbles have been introduced. So with those two bubbles, the instruction view would look like this. That there is a first bubble introduced. It's not going through IM and RF stage, but it gets introduced from ALU stage onwards. No op 2 is introduced here, and this is the I plus 1 instruction. So fetching was done here, then did nothing for 2 cycles, remained stuck there, and then it is in this cycle it is reading from register file. Instruction I plus 2 could not be fetched here, could not be fetched here, it gets fetched here. Okay. Okay.
Sir?
Yeah.
So the previous lesson here, basically the I mean the IM, RF, ALU, this entire set remains constant for every instruction.
Yeah, every
We
instruction goes through the same stages.
okay.
Yeah.
And so then this one gets gets incremented by 1 every time the new instruction comes in.
Yeah. So yeah, one new instruction came in here. Uh, this instruction comes in after a gap of 2. Okay, this instruction came immediately. I+1 came immediately but remained stuck. So since it is stuck, the next instruction cannot come in.
Okay, so got it. I mean that this means this is controlled. Like when the next instruction will come in, it is not
Yeah,
like
yeah.
coming at
So
every
we have
process.
not discussed the control yet, how we achieve this. What we are looking at is what we would like to happen.
Okay, got it.
So how do we handle hazards? So handling in hardware, how we design our circuit. We need to detect instructions with data dependence. That means uh, if there are 2 instructions, one writes into a register and second one reads from that register, then uh, this is a cause of a hazard. So we need to detect this kind of sequences. Then we need to introduce no-op instructions or bubbles in the pipeline. There is a more complex approach which tries to cut down on the delay is what is called data forwarding. We will see that shortly. For handling control hazards, we need to look at instruction and see if they are branch instructions. Uh, if branching has to occur, then we need to flush the instructions which would have entered the pipeline. Okay, suppose we are continuously entering instruction in the pipeline and the branch has to occur. Okay, then what has come into the pipeline is incorrect and we have to throw that out. A more complex approach which reduces the delays is branch prediction. That means uh, we could take some action ahead of time. We can, if we can predict that yes, this branch is going to take place, then we can start following execution at a different point. Okay, but that needs some prediction in such a manner that we should be correct most often, and we should be prepared to undo things in case we go wrong. Okay, so we aggressively try to follow certain path, but we have a mechanism to undo things in case uh, something goes wrong, our prediction goes wrong. Is there anything we can do in software to cut down the delays due to these hazards? Uh, Sometimes it is possible to reorder instructions. Okay, and if we can reorder our instruction such that the dependent instructions are not next to each other, then we can cut down on these hazards. So a compiler can do this job. Uh, it can, between 2 dependent instruction, it can put an independent instruction, 1, 2, or more as required. And there are also, it is also possible to leave the entire task of data hazard removal onto compiler. So suppose you have a processor where you have absolutely no provision for handling data hazard. Okay, it assumes that the code is data hazard free. Then the compiler will try its best to put independent instruction between dependent instructions. And if it cannot find such instruction, it will have to insert no operations. Okay, so that the code can run without any need for data hazard detection by hardware and insertion of delays. For branches, uh, what we can do is we can organize our hardware such that the branch is a delayed branch, in the sense that after branch instruction, you always do one or two instruction in the sequence and branch only after that, by the time your uh, branch decision is taken and target address is calculated. Okay. So what could be those instructions? Those instructions should be there such that they have to be executed in either case. Okay, whether the branch condition is true or false, if those are the instruction which always need to be executed, you could put those after the branch instruction. So those are called instruction in the delay slot. So branch always takes place after that delay, and there are instructions which are always done irrespective of whether you branch or not. Uh, I mentioned data forwarding. Let me explain what it is. So again, back to an instruction which writes into R6 and another instruction which reads from R6. We uh, we have this instruction I going through these 5 stages, and the vertical axes indicate time. The next instruction is one step later. It needs value of R6 actually in its ALU stage. And here this is an add instruction which is producing some result that has to go to R6. So can we transfer the value directly? The result of this addition, can it be transferred as an operand to the next instruction without having to go through register, without having to be written into register file and then read from register file? The answer is yes. How we do that, we'll see later. So the output of this ALU is being passed directly to this. This is same ALU, but now it's being fed back to the ALU for the purpose of next instruction. Okay. So this is one possibility. Another possibility is that suppose R6 was being filled by instruction like load. So the value to be put in register file is coming at the end of this stage, DM stage. Then it is from output of DM data memory, we like to feed into ALU. So again, we are trying to bypass register file, but in this case, instruction still needs to be delayed by one cycle. So we are cutting down a cycle by doing this data forwarding. Okay. Here I'm showing a case where instruction I needs to compute R6 and that value is read by instruction I plus 2, not I plus 1. So I plus 2 will be coming 2 stages later, 2 time slots later. And when ALU needs this value, this would be stored not at the output of ALU, but it will be at the next stage, the pipeline register, which is after DM. Okay. So it needs to be forwarded from that point onwards. Let me indicate what I mean by this. See here, when output of ALU is to be used as an address in the data memory, it's available here. But if it is to be written into register file, it is delayed by one cycle as it passes through this register. Okay, so when I said that you need to forward output of that add instruction to the next add instruction. It is from here out, from this point you forward to this input. Okay, when you are forwarding from ALU to ALU, it is actually this value from here, from this point, you are forwarding to this input of ALU or that input of ALU. The second case I showed was we forwarded output of memory from this point, output of this register from here to this input or this input. And the third case was forwarding from here to this input or this input. Okay. There is one more case I will show.
So like, can you explain again why in the third case we can't do like the first?
I'll come back to the same diagram. Let me look at one more case. So this is, I'm calling it data forwarding path P1 from ALU to ALU. So it could be this input of ALU or could be that input of ALU. R6 could have been the first operand or second operand. Second, I'm showing value read by load instruction from memory that is being forwarded to ALU. And third is from output of ALU, but after this stage to the input of ALU. And there is one more, there are two more cases, which I'm calling path P3, where you're forwarding it to a store instruction. Okay, from this is from add to store. So it is from here to data memory input. And in this case, it is from load to store. So it is from output of DM to input of DM. So let me now go back to the design. Yeah. So various cases which I've talked of is you need to forward the data available here. So although I'm using the term data forwarding, it means the path going back actually in the pipeline. So forwarding in another sense actually. So there has to be a path going from here to the two inputs of ALU, which means actually we'll have a multiplexer. So ALU can take either this data coming from here or will take data coming from here. Then there was a case of forwarding from load to add. So from here, there is another path going here or there. Then add to add with a gap of one instruction. So ith instruction produces a result. I plus 2 instruction needs that value. So it is from here to one of these two inputs. Then the next cases were that from add to store. So it was from this point to the right data. Okay. So store instruction requires register value coming here, and so we have path going from here to here or from here to here. So in the next class, I'll actually have figures showing these paths, but I thought I'll just indicate it this way. Any question?
Sir, is the are the like if the processor design does proper insertion of the non-codes for skipping data clashes and all of that, are they in the instruction defined in the instruction set only? Because if a compiler needs to do that itself, then the compiler needs to be aware of the design of the processor and not just the instruction set.
Yes. So if you are writing a compiler for a machine which doesn't have data hazard detection capability, the compiler must know that and generate code accordingly. So compiler has to be aware of that.
So in the assignment stage one, we have to implement the register file. So can we do in the same way you explained today, like read in the rising edge and write in the falling edge, like
No,
both
no,
opposite?
no. I think in the lab we are not building a pipeline processor. That is, I think,
Okay, okay,
that's
okay,
much more complex. So you're building a simple, eventually multi-cycle design.
okay, okay. So
So we don't worry about that aspect. Okay, we'll stop here.
sir,
And sir,
Yeah.
is there
sir,
any uh, hello? Is there any recommended resource for learning VHDL or from your side, like
Uh, so which book you are following in your logic design course?
um I don't remember the name actually. It was something containing fundamental logic designing with VHDL. The name was something like this.
Yeah. So I think the VHDL there, which you learned there, should be adequate. And see, once you picked up basics there, then for reference we can use reference documents, and I can
Okay.
post such a document uh, on Moodle.
Okay, so thank you, sir.
so I have a question. So when we are saying we are creating bubbles, so how does a matlab, how does the
How
microarchitecture know about it? So the next variable is R6 if we are accessing. So
Mhm.
do we use do compiler tell this?
no, bubble creation, that's a hardware issue. So there should be some logic in your design which looks at the instruction operands and results and figures out there is a hazard and a bubble needs to be created and should create a bubble. So all that is the role of the hardware.
Okay, so
What software can do is to uh, separate out such instruction pairs which can cause hazard. Okay. All right, we'll stop now.